So, got a very exciting unit for you guys. It's exciting because you're going to witness the power of mathematics. Okay? So we're doing a unit called Deductive Geometry. Okay? Now within logic and further, by extension, within mathematics, there are two types of reasoning. We have deduction and induction. And we're really going to uncover the difference between these. Because in this unit we're using predominantly deductive geometry. And what that means is if our argument is true, then our answer is necessarily true. The maths here is not going to be challenging, the content's not going to be challenging, but the difficulty in this unit lies in the number of potential ways that a question could possibly unfold. So the stuff we're going to be doing is not hard, but there are lots of possible paths that you could take, and only perhaps one or two of them might lead to the answer. So we're going to need a bit of foresight in using this maths. And it is a short unit. If you look at the teaching of it, I think there's about 3 weeks of teaching. And then we've got some time to work on our assignment, which is based around this stuff as well. So I am going to get just straight into it. We're going to start with our notes booklet. So we've got 2 booklets, okay? And the reason is, again, the textbook does a pretty poor job of the deductive geometry unit. We may refer to it for some challenge questions, but for now we're going to just keep looking at the work booklet. So you've got a notes booklet and a work booklet. We're going to just start with our notes booklet here. And we're just starting with some basic Year 8 geometry. But we're going to prove some of the theorems that we use in Year 8 geometry. So we're going to really investigate what is the nature of proof. So we have, by definition, right, a full revolution the whole way around is 360 degrees. And this is just arbitrary, okay? It could be 1,000. All right, you could cut it up into 1,000 pieces, but it is. It's like a pizza that we cut into 360 pieces. Why do we use 360? I reckon I told some of you last year.
It's a lot of factors.
Pardon?
Is it because it has a lot of factors?
It has lots of factors. So go back to Babylon. They used a base 6 counting system. We use base 10, right? So you go up to 10, and then it repeats, doesn't it? You go 1, 1, 1, 2, 1, 3. That's 11, 12, 13. So Babylon, they had base 6, and 6 goes into 360, so that's where it comes from. But yeah, 360 is divisible by every number from 1 to 10 except 7. So there's lots of factors that make it up, and that's why it's quite useful in that regard as well. Anyway, it is arbitrary. So if we have 360 as a whole revolution, that means a straight line is 180, and it means a quarter turn is 90. All right, nothing outrageous going on there. We know that half of 360 is 180, and half of 180 is 90. So that's what we're going to start with. Okay, given 2 intersecting straight lines, prove that vertically opposite angles are equal. So you'll remember this theorem from Year 8. If this is angle A, then this is going to be angle A. Now you're just told that. You're told that, and then you apply it. All right, but today we're going to prove it. So the way we're going to set out a proof is we've got these lines. We're going to have line A, B, and line CD, and let's say that they intersect at I intersect. Okay, so you're going to, where I've written proof, that's where you're going to lay this proof out, and we're going to go through it all together. So what I'm going to do is I'm going to say, let angle AIC equal alpha. So we're just going to come in here, we're going to define that as alpha. We can do that, that's fine. Now, we know that angles on a straight line add up to 180 degrees. I'll leave the idea. And so we can see that CD is a straight line. And so that means this angle here is going to be 180 take away alpha. Okay, because that's a straight line. Angles on a straight line are 180 degrees. This is alpha, so this is going to be the remainder after we subtract alpha from 80. So let's write that. Therefore, angle AID, all right, remember AID, that's telling us this angle, is equal to 180 take alpha. Now, whenever we make any statement in deductive geometry, whenever we make any statement that we've derived from information we have, we must provide a reason. And so our reason here is angles on a line. Okay, angles on a line add up to 180 degrees. Excellent. But then we can see AB is a straight line, isn't it? From A to B, that's also a straight line, which means this angle here is going to be 180. Take away this angle here, 180 take alpha. So let's write that out. Therefore, angle DIB is equal to 180 take away 180 take alpha. Again, the same justification, because angles on a line are 180 degrees. And so if we process that, we've got angle DIB is equal to alpha. And so we can see angle AIC, therefore angle AIC is equal to angle DIB. Both of these angles are equal to alpha. And so it doesn't matter the size of the angles. If we have two straight lines and they intersect, opposite angles are equal. All right? Proof. Okay, so we started with something like this. A straight line is 180 degrees. And then we've managed to deduce, all right, by deduction, that opposite angles are equal. Okay? This angle here, we can see, again, by extension, is going to be 180 take alpha as well. There's alpha right there. So there's our first proof. Okay, so then we've got angle theorems down the bottom, and I've left a table there for notation. Because when we're using these theorems, we need to reference them. And we don't want to be writing out because vertically opposite angles are equal or anything like that. We want to come up with some shorthand notation. And we want to all use the same thing just to make sure we're all on the same page and we can understand what's going on. So with notation now, I'm going to get you to fill in those three columns. Okay, in the first one, we're going to just write vert op angles. Okay, so if we use that, it means we're using the justification that vertically opposite angles are equal. Our second notation is angles at a point. All right, one revolution is 360 degrees, therefore if all angles are meeting, this section plus this section plus this section, it all adds up to 360 degrees. And then our last one we've used already, angle on the line. They're our 3 points. Okay. Now I would like to rub it all out and use that space again. Is anyone still writing it down? Excellent. Okay, so now we're looking at some parallel lines, and this continues again what we were doing in year 8. So we might start with this idea of an axiom. So an axiom, it's a cool word. It's something that we cannot prove, but we assume it to be true, and then there's an abundance of proofs that are going to flow from it. So let's say I've got these parallel lines, okay? And a good way to draw parallel lines might be like if you have a ruler, all right, and it's a straight ruler, you know, put it up like that, and you just draw on either side, and you know that they're going to be parallel. Now, what do parallel lines mean? It means they've got the same slope, means they're going in the same direction, means they're never going to meet, means they're the same distance apart at every point along, the same distance apart. Okay, so I've got these parallel lines here. And I might go, oh, let's check out this angle here. And I could pull my protractor out and measure it. Okay, if I was to pull my protractor out, I might say, oh, that's about 60 degrees. And then I go, well, that one looks quite similar. It looks like it's a similar angle. And I could pull my protractor out and measure it. And I could see that they're both 60 degrees. And so then I might come up with this hypothesis. Well, I reckon if these angles are in the same respective location, then they're going to be equal. That's going to be my axiom. And then I'll say, all right, well, let's draw another set of parallel lines. Let's do it like this. And I go, well, now look at those angles. They still look like they're the same. We can measure them. And so we're coming up with a hypothesis that if we have angles that are in a corresponding location, they are equal. That's going to be our axiom. Okay? Corresponding angles in parallel lines, are equal. That'll do for now, and we'll simplify it a little bit later. Okay, so if we start with this axiom, we can prove all other properties of parallel lines. This, however, is not something we can prove deductively. We can only prove it inductively. And so that means we can keep doing it over and over and over again for an infinite number of circumstances. You can do it 1,000 times and check that it's right in 1,000 circumstances, but it doesn't prove it in every case. It's only proved it in 1,000 cases. Okay, you can do it in 1,000,000 cases. It doesn't prove it in every case, only proves it in 1,000,000 cases. So perhaps we're starting to see the difference between deduction and induction. All right? So we've got corresponding angles are equal. That's our first rule. So then I might say, all right, well, if that's the case, and let's again do some labeling here. We're going to have A, B, C, D, E, F, and G. There's one more. All right. Now I'm going to say. Now, has it already been drawn for you guys? No. So we're on to co-interior angles are supplementary and alternate angles are equal. They're the two that we're going to do. We're going to prove these two theorems now. Now we can see, let's let DBC equal alpha. Okay? Now if this is true, alright, now let's apply our axiom. If this is alpha, then angle FDE is going to equal alpha as well. Okay, that's going to be alpha as well because of corresponding angles. All right, but now we can see that this line here, F through D through B, that's a straight line, which means this angle in here is going to be 180 take away alpha. So let's make that statement. Angle, let's call it BDE. Angle BDE is equal to 180 take away alpha. How do I know that? That's because angles on a line are 180 degrees. Here's a straight line. This is alpha. This is 180 take alpha. And now look at this. If we have angle CBD, or how did we describe it previously? DBC. So let's make sure we use the same notation. DBC plus angle BDE. What we're going to have is we're going to have alpha plus 180 take away alpha. Okay, if I'm adding this angle here plus this angle here, we've got alpha plus 180 take alpha. And it's going to simplify to be 180 degrees. And so we have another proof, okay, that angles inside parallel lines are going to add up to 180 degrees. If this axiom is true, and we've got good evidence to believe that it's true, if it's true, this is what we're basing our whole mathematical theorem on. If this is true, then so is this, that angles inside parallel lines are supplementary. So we'd make that statement. Supplementary meaning they add up to 180 degrees, okay? So angles in parallel lines are supplementary. Okay, I might pause there because I think you can probably do the last proof by yourself. Okay, that alternate angles are equal. So what does alternate angles are equal mean? Well, look, here's our parallel lines. this angle and this angle are equal there on alternate sides of the parallel lines. Now, before you go ahead and do that, make sure you structure it in the manner that I've been doing. Okay, so we dictate points, we define an angle, and then we use this axiom plus some of the other properties of lines we've already derived, that opposite angles are equal. Give that a crack. Okay, I reckon you'll be able to do that. Give that a crack.